Okay, so good afternoon, everybody. So my name's Stephen Lynch. I'm a lecturer a reader at Manchester Metropolitan University. I've written a number of books based on Python, MATLAB, Mathematica, and Maple, and I've been using most of those packages for many, many years. In 2022, I was made a National Teaching Fellow based on my work with widening participation, and I run national workshops teaching Python to A-level maths pupils, especially those from a poor socio-economic background. I also won the award for developing a programming-based curriculum at MMU. And finally, all of my research feeds back into my books, and then also feeds back through to the teaching. Recently, I was contacted by Scholar GPS. I'm not sure if any of you have heard of this Scholar GPS, but apparently I'm ranked number 23 in the world for dynamical systems. So that was nice to discover the other day. Okay, so the aims of this talk, I'm going to explain how programming, computational modeling, and simulation can improve the student experience. The picture on the right is a picture of the new lab. So MMU have just built a £150 million building for science and engineering, and we have these active learning studios with the interactive boards, and you can see the kind of setup, which is perfect for the kind of programs that we run. So I'm going to provide, we want to provide the tools for our students to become highly employable. We want to provide resources for our students to use those tools. And we're going to provide extra and co-curricular programming workshops for all staff and students right across the university. So you can see from the logos there, at MMU, we use Python, TensorFlow for artificial intelligence, MATLAB, and R. So this shows you the option map for mathematics at Manchester Metropolitan University. So in the first year, which we call level 4, we do discrete maths, development and employability, probability and stats, calculus, decision maths. Well, the most important unit on our degree is this linear algebra and programming. So in this 30 credit unit in year 1, we introduce our students to both Python and MATLAB. Okay, and we think there are several benefits to this. So introducing students to programming who've never programmed before can be quite intimidating. But if you do it with 2 different languages, it kind of cements the understanding. Some students prefer Python, some students prefer MATLAB, so that's an interesting dynamic as well to see which is the most popular with our students. In the second year, you'll see we do further linear algebra, numerical methods and modeling. Obviously, we do a lot of modeling with MATLAB and Python there. In the probability and stats, we also introduce our students to R, the R Studio, and we continue with the R Studio with stats and financial maths. And then the number theory and abstract algebra, I think the lecturer there does a little bit of Python. You saw series examples with group theory, so you can introduce that there. Where our degree really comes into strength, so is in the final year. So we do have these programming languages right through the degree, but in the final year we use them extensively. So obviously computational methods in ordinary differential equations, applied regression and multivariate analysis. My unit, so this is the unit I'm going to concentrate on today, which is the dynamical systems and chaos. So I teach this in both Python and MATLAB. We have advanced operational research, obviously numerical methods for PDEs, again, relies a lot on computational work. And then the final year, our students have a compulsory project, a 30 credit project. And for those students who like programming, they can do a programming based unit based on either Python or MATLAB. Or as Kevin pointed out, some students do not like programming, so they could choose, if they wanted to, they could choose, a completely pure-based project or just avoid programming altogether. That's fine. If our students don't want to do any programming, they can do that in their project. This is a very popular degree. So at MMU, I think currently there are over 41,000 students and over 500 courses. I think it was about 12 years ago, the Students' Union started running a competition with the students to see, who's the best teacher, what's the best course. And you'll notice that mathematics has actually been shortlisted as best course in the whole university 8 times. And unbelievably, mathematics won in 2012, 2018, and 2020. So programming on a maths degree is very, very popular. Okay, so how do we access Python in particular? So there are many platforms. If you look on the internet, there are lots and lots of ways to access Python. At MMU, we use Python idle. That's useful for things like Raspberry Pi, and a lot of students who've been introduced to Python at school will have been introduced to Python idle. For scientific computing, for the kind of computing we need to do at university level, we really need to use things like Anaconda. And I've got so we use Spider, which is very similar to MATLAB, and Jupyter Notebooks. We also use Google Colab, which is cloud computing. And the major advantage with Google Colab is you do not need any software at all on your computer. So this is really, really good for equality, diversity, and inclusivity. Okay, so we have a massive library with lots of computers with not specialist software on it. So our students can go and program Python on any computer as long as they have access to the internet. They don't need to download any software at all on their own computers. Okay, so this year I taught on foundation computing. There were 350 students on the course. So these are students who didn't quite get their A-level grades, who want to do either computing or a mathematics degree at MMU. So they have to do this 1-year course. And one of the units they study is Foundation Computing 2. And as you can see, I run this unit and it's called A Simple Introduction to Python. So I wrote a book to go with this unit. In week 1, and you'll see each week it's a 15-credit module. Each week we have a 1-hour lecture followed by 2 hours in the lab. So typically there are 150 students in the lab with 4 members of staff, and we circulate and help the students talk to the students. So in week 1, I introduced Python as a powerful calculator, because all students, well, I think everyone, can use a calculator, just pushing buttons. So in the first week, I just show them how they can use Python as a very powerful calculator, and we have fun. I'll show you some of the fun things we do there. Then I introduce them to programming, and I assume no programming knowledge at all. So there are only 3 programming constructs. I show them how to define a function. Again, I use very simple examples. I show them loops, for loops, and while loops, and then finally if, elif, else constructs. And with those 3 constructs, you can write any program. And then again, to introduce a fun element, in week 3, I introduced them to the Turtle module, which is a bit like Scratch, and I'd say about 50% of our students at MMU have seen the Turtle module in school. So the Turtle module is using Python to draw pretty pictures, and this is the week that I give out a coursework. So this unit is 100% coursework. There is no examination in this unit. Week 4, I introduced them to numerical Python and Matplotlib. Week 5 is Google Colab, Symbolic Python, and GitHub. So I show them how to produce notebooks in Python, and their coursework assignment is actually producing a Google or Jupyter notebook, and then they have to save that as a PDF, and they submit their notebook as a piece of coursework. I also introduced them to LaTeX, so I show them how to create mathematical equations for this notebook so it looks professional. In week 6, I do Python for mathematics, and I go over the mathematics that they do. So they do Foundation Maths 1 and Foundation Maths 2 in the foundation level year, and I do the Python that covers that foundation level mathematics. So again, hopefully that is reinforcing their learning of the mathematics. Week 7, I introduce them to cryptography. Week 8 is an introduction to artificial intelligence. Week 9 is an introduction to data science using large data sets. That I'd say 50% of the students had seen these large data sets when they were doing A-level maths. So large data sets are being used at A-level. And then finally, in the last week, we introduced them to object-oriented programming. And then in week 11, I just show them, all of the degrees that we offer at MMU. I can tell you that next year, we are going to be taking 800 students onto the first year of the computer science course, and there will be about 40 students on the mathematics course. So those are the kind of numbers we're dealing with at MMU. Okay, so this is a book that was published last year, and I gave a link for my webpage, so you can find all of the resources for all of these books on my web pages. So last year I wrote a book entitled Python for Scientific Computing and TensorFlow for Artificial Intelligence. For many years I've been going around the world, running these workshops in China, Malaysia, Singapore, USA, and recently Saudi Arabia. But I also offer this as either a 5-day intensive workshop or a 4-day intensive workshop at Manchester Metropolitan University. So the workshop is completely based on this book. And a good thing about CRC Press is the university can make an institutional purchase of the book. I think it costs about £200 for an institutional purchase, but then every single student and every single member of staff within MMU can then download this ebook for free. So again, this really helps with equality, diversity, and inclusivity. All of the students get the book. I also maintain web pages where they can download all of the programs, and I have pages where I produce notebooks and publish them as web pages, and I'll show you some of those again later. Okay, so you'll see that I assume no prior knowledge of Python or programming. So in a nutshell, students learn how to program in Python. They can apply Python to scientific computing, and I'll show you which disciplines in a moment. They are able to solve real-world problems. They can understand how the brain works. I upskill to artificial intelligence, because obviously artificial intelligence is going to permeate everything for many years to come. And at MMU, we have this RISE initiative where the students can study that there's lots of subjects they can choose from. This one is the Python workshop. And if they attend all of the lessons, and I think they have to write a short report, they will be awarded 300 RISE points, which will appear on their transcript when they get their degree classification. So what's in this book then? So section 1 is an introduction to Python, and there's also 2 chapters on an introduction to Python for A-level mathematics. So for about 5 years now, I've been running these workshops, Python for A-level mathematics and beyond. And I'm trying to get Python introduced to the A-level mathematics because I think it will introduce a fun element into A-level maths. I'm sure you're all aware A-level maths is the most popular A-level in the country, but when it comes to choosing subjects at university, mathematics is one of the least popular subjects at university. And I believe that if we introduce programming, make it more interactive and more fun, I think we can encourage more students to want to do mathematics at university level. Section 2 shows you how you can use Python for biology, chemistry, data science, economics, engineering, in fractals and multifractals, image processing. There's a chapter on numerical methods for ODEs and PDEs. I know Siri had a really nice example of the PDEs, physics and statistics. So another thing I do at the university is my aim is to teach every undergraduate and every member of staff in the university how to code. I believe you can teach everybody how to code. Section 3, obviously, a lot of people use artificial intelligence or they want to know what this artificial intelligence is. So the final section is a very simple introduction to artificial intelligence. I also so the introduction talks about my invention on binary oscillator computing, and then I show how neural networks work, neurodynamics, and then there's some really nice examples of recurrent and convolutional neural networks. And if I have time at the end, I will show you how you can use long short-term memory, recurrent neural networks to predict chaos. And it predicts chaos remarkably accurately. And of course, you can also use it to predict financial time series data, and you can predict any time series data. So this book was published by CRC Press in 2023. Again, there's a GitHub website, so you can download all of the Python files and all of the notebooks, and there's also web pages. So there are exercises in the book. I do tell students to attempt the exercises, but there are full worked solutions also available online. Okay, so now I come to the meat of what we're doing today. So what about my final year unit? So the unit is called Dynamical Systems and Chaos, and it's based on my books, Dynamical Systems with Applications Using Python. Now the book, I think it's about 25 chapters long. You couldn't cover the whole book in one unit. And so there are topics in this book which are suitable for master's level. And you can see here, I've taken 10 of the chapters, and these are suitable for final year undergraduate mathematics. So in weeks 1 to 5, I cover continuous dynamical systems, and in weeks 6 to 10, I cover discrete dynamical systems. So in week 1, I start with solving linear ODEs and plotting phase portraits with Python and MATLAB. Then we'll move on to nonlinear phase portraits. Then so my original, so I did a degree in pure mathematics, and I was trying to solve the second part of Hilbert's 16th problem. So I was looking at limit cycles. So limit cycles are the most common form of solution when you're modeling planar systems. We look at Hamiltonian systems and Poincaré maps, Lyapunov functions and stability, and three-dimensional systems. Siri showed you we can plot really nice three-dimensional images, and then we can actually rotate those images as well in Python and MATLAB. And the main thing is we look at applications. So how can all of this theory and the programming be used to solve real-world problems? For the discrete systems, we look at the tent map and the logistic map, and obviously population dynamics for the logistic map. Then we look at two-dimensional discrete map and applications for those 2D discrete maps. And then in week 8, I give an introduction to artificial intelligence, but using the theory of dynamical systems. Then I show the students, it was nice that Siri showed the example of the complex mappings. So in week 9, I show our students how they can use complex iterative mapping to model the propagation of light waves through simple fiber ring resonators. So again, it's about solving real world problems with this mathematics. And then in week 10, I introduce them to fractals and multifractals, show them how you can produce very pretty pictures with Python and MATLAB. But also there are big applications, and again, I'll come on to that a bit later. And then week 11, we go through past papers and that kind of thing. Okay, so I do make a software readily available for this unit. So it's a 30 credit unit with 6 hours contact per week. So typically there are 2 hours of lectures and 4 hours in the computer lab. So the majority of time is spent in a computer lab with the students writing simple programs, playing with the code and trying to model real world systems. So there is an online Jupyter Notebook, and at the end of the talk, I will show you my web pages. I'll show you, how you can use Python to cover the whole of the syllabus. Just while I'm talking about web pages, I've also written a Jupyter Notebook which shows you how Python covers the whole of the A-level mathematics syllabus as well. And then for MATLAB, so the MathWorks, I've got the MATLAB Central File Exchange. So all of my MATLAB programs are available to download for free. So again, equality, diversity, and inclusivity. So students can access all of the code for free. And I've just completed writing the 3rd edition of the MATLAB book. So Siri, this is something for you to look forward to. I think it's about a 10-year cycle. You write new editions of these books. So with MATLAB, with all of my packages, I produce 2nd and 3rd editions on a 10-year cycle. So the 3rd edition of Dynamical Systems with Applications Using MATLAB is due to be published in, I think it's October 2024. And currently that book has 600 pages, and I think there are 25 chapters in that book. Okay, so now I'm going to talk about assessment. So for my final year unit, 40% of the unit is assessed with coursework. Now, coursework is invaluable because this is where we can get the students to solve real world problems, and we can ask them to write long pieces of code. So here's an example where I've got a 3 neuron module. So these are called neuron modules. We have X is a neuron, Y is a neuron, Z is a neuron, and we have excitatory connections, which is shown in green, and inhibitory connections, which are shown in red. So and you can, I give them a 3-dimensional discrete model which models this system. So there's all kinds of mathematics you can add. How many fixed points does this system have? What is the stability of those fixed points? So these are the kind of problems that you can ask your students at most universities. But then because they can program, we then ask more in-depth questions. So this is a really nice question that I asked the students. So we want to know, how does so they can plot a bifurcation diagram for this as one of these weights varies in the model. Now, again, you can individualize the coursework by giving different classes of students, what happens if weight W21 increases and decreases, and then you can ask another cohort of students what happens if W23 increases and decreases, etc. So we use the second iterative method where we use feedback. So we feed back into the system, and I'll explain what that is in a moment. And you'll see this one question is worth 25 marks. So there's lots of mathematics, and they use Python to answer the mathematical equations, but then they have to write a longer Python program to plot this bifurcation diagram. Okay, so they typically have 4 questions. So that piece of coursework is worth 100 marks. They typically get two questions in discrete mathematics and 2 questions in continuous mathematics. Now, a lot of you are probably thinking, oh, I'd really like to see those questions. So in my books, I have examples of coursework questions. I think there's about 20 examples of coursework questions for continuous systems and for discrete systems. Now, another part of the unit assessment is a traditional examination, except for this is not a traditional examination. So we have a 3-hour examination for dynamical systems, but the examination takes place in a computer laboratory. Okay, so it's a 3-hour examination, but the difference is here that we don't ask the students to write long programs. Okay, it's not suitable. So this environment is not suitable for writing long programs. So what we do instead is we get the students to use MATLAB or Python as a powerful calculator. So for example, computing eigenvalues and eigenvectors and things like that. So it's kind of a traditional 3-hour examination paper, but we can give them more, more difficult question to solve because they have Python or MATLAB, to do the numerics and solve differential equations, etc. So for example, this is a typical question. They're asked to solve an initial value problem where you've got dr by dt is minus r cubed over 2, d theta by dt is 1. They're given initial conditions, r at 0 is 1, theta is 0, 0, and they're asked to derive the Poincare return map, mapping points on the positive x-axis to itself. Now, again, you're probably thinking, oh, I wish I could see more of these examination type questions. Well, in my books, I currently have 3 whole examination papers. So there are 3 kind of mock examination papers where there are 8 questions, and the students are required to answer 5 out of 8 questions in 3 hours. So each question is worth 20 marks. Okay, so what do these programs look like? So in the first week, I introduced the students to differential equations and planar systems. So I show them this program. So I give them this full working program, and I say this is in the book. But I go through the syntax with them. So you'll see in Python we have to load some libraries, or sometimes they're called modules, and we use we use name placeholders. So PLT is used for matplotlib.pyplot because matplotlib.pyplot is a bit long. So we use the alias PLT instead. For the numerical Python library, we use the alias NP, etc. Here is our linear system of differential equations. So we have dx by dt is ax plus by, and dy by dt is cx plus dy. So you can see it's just a simple linear planar system. This part of the program solves the system numerically and plots the trajectories forwards in time. So you can imagine, when you go through this program, you're having to explain all of the mathematics as well. And Siri shows some really nice examples of this. And then we can also plot the trajectories backwards in time. And the students love this. The thought they can actually go backwards in time. So this is the code where we can actually take the trajectories backwards in time. And then I show them, how to label the axes, because obviously when they do presentations, etc., all the font sizes have got to be the correct size. And then we can do a vector field plot. So again, I give them the program for this. But what's good about this program now is you'll see that this is very easy to edit for the students. All they have to do is change the A, the B, the C, and the D. And you see in Python, we can assign variable names in one line. So A is 2, B is 1, C is 1, and D is 2. So the students can easily just change those numbers and they can obtain different phase portraits. So here's the phase portrait for dx by dt is 2x plus y, and dy by dt is x plus 2y. And just like Siri did, you can easily use Python or MATLAB to determine eigenvalues and eigenvectors. So for these linear systems, you'll see that we have two of the manifolds are, two of these sets of trajectories are straight lines. So these, well, in this case, we have two unstable manifolds, and they are given by the eigenvectors. So, we can use these commands. So within the symbolic Python library, we can define a matrix. We can evaluate the eigenvalues, and we can evaluate the eigenvectors, and then geometrically we can actually show what those eigenvectors represent. And of course, we've also got the vector field, and we can talk about trajectories going forwards in time and trajectories going backwards in time, etc. Okay, now I'm going to start showing you the real power of Python and MATLAB, and this is similar to what Siri was doing. So now we're going to look at limit cycle bifurcation. So during the dynamical systems, I show the students the Fitch-Nagumo model of a neuron. You can see it's a planar system, and IT is the input current into the neuron. So the way I explain this to school children is, here's our neuron with the head of the neuron. We input current into the neuron, and you reach a threshold where it starts to oscillate, and then it gets faster. And as the input current goes in, the neuron oscillates faster and faster and faster, and then it switches off again. Okay, so I'll show you that one more time. That's how I should explain it to school children. You input current into a neuron, nothing happens, it's at resting potential, and then you get to a point where it kind of starts to flicker, and then you reach threshold where it oscillates, it gets faster and faster and faster, and then goes off again. Okay, we can also show this with phase portraits. So here we are increasing the input current from 0.1 to 2.5. So if I run this animation, you'll see you've got a critical point, goes into a limit cycle. The limit cycle represents an oscillation, and then that disappears again. Okay, so we increase the input current into the neuron. It's at resting potential, then it starts to oscillate once we reach the threshold, and it goes back to a single point again. I can't show you this interactively, but this is really great, for the students. If you've got an interactive whiteboard, you can ask them all kinds of questions, and the students can come to the front and they can move the sliders left and right, to see what happens to the solution curves. Okay, in week 5, I show them how you can use Python and MATLAB to model electrical circuits. So this is Chwa's famous electrical circuit. So we have linear capacitors, linear resistors, and a nonlinear resistor. We can simulate this with Python and MATLAB. And this is a really nice example because we can actually build this physical circuit and connect it to an oscilloscope. That's the solution you can see on the left. And of course, we can solve this numerically with MATLAB and Python, and we can plot the numerical solutions. And again, we're increasing current in the circuit, and we can actually see how the input in the circuit changes as we change parameters in the circuit. Okay, now in 2001, John Borison was an undergraduate at MMU, and he came to see me because he was fascinated by Chwa's electrical circuit. I'd showed him all these animations, and he wanted to do his final year project on Chwa's circuit. I had to say, sorry, John, we don't have a physics department anymore. believe it or not, MMU closed physics in the 1990s, but locally, because of Python and MATLAB, we could do simulations. So I said to John, I do lots of research with hysteresis. So I said to John, why don't you investigate Schwarz circuit and see if there's any hysteresis in Schwarz circuit? So he went away and he was writing in MATLAB, and within a few weeks he was able to find hysteresis in Schwarz circuit. So we quickly put together a journal paper, we submitted it to the International Journal of Bifurcation and Chaos, and the editor for that journal is Leon Schwarz. So this is a fantastic story to tell our undergraduates. You know, John was an undergraduate at the time. He's a lot older in this picture, but as an undergraduate, he had a journal paper published. Then he went on to do a PhD, and then he returned to MMU, and he's now my co-inventor. So the picture on the left is a picture we use to represent our invention, and it's called binary oscillator computing. And again, the results of this invention are only possible because of MATLAB and Python. So the picture on the left shows a binary oscillator half adder. If you want more information on this, yeah, I'll show you at the end. There are chapters in my books which explain this. The picture on the right shows a binary oscillator set reset flip-flop. So we can perform logic and we can store memory with threshold oscillators. So our plan is to replace transistors with threshold oscillators. And we've made some exciting developments, and we're working with all kinds of people all over the world, and we're currently setting up our own company, and we've got lots of interesting examples. So the students love this story. We have a very simple idea in mathematics, and potentially we think we can build the world's fastest supercomputer. And we're also working in medicine, making logic circuits out of human neurons, and also making memory circuits out of human neurons. And again, if you want to know more about that, you can read my books. Okay, and so when we were looking at set reset flip-flops, one of the devices we want to replace transistors with is Josephson junctions. So Josephson junctions are devices in physics which are superconductors. So you cool them down to 4 Kelvin, which is minus 269 degrees centigrade, and they become superconducting. They are natural threshold oscillators, just like neurons in the brain. So the average human brain has got 100 billion neurons, and those neurons oscillate 1,000 times in 1 second. Well, these Josephson junctions oscillate 100 million times faster than neurons in the brain. And what we've recently discovered is we're building set reset flip-flops out of these Josephson junction neurons. And we've discovered that the two states, the set and the reset, the most stable state for this system is when we flip between a small amplitude limit cycle and a large amplitude limit cycle. Now, again, this is a fantastic story because I did my PhD on the second part of Hilbert's 16th problem, which is all about, you know, how many small amplitude limit cycles does a polynomial system have, and how many large amplitude limit cycles can a polynomial system have. And you can see here, so this system, this is the Morris-Lacar model of a neuron. So this system can have 3 limit cycles. You can have a small amplitude limit cycle and a large amplitude limit cycle. So for our invention, you can actually switch. So the set and the reset set are between a small amplitude and a large amplitude limit cycle. That is more stable than having a limit cycle off, or a neuron off and a neuron on, which is a surprising result. And another very recent result is, so in order to use these set reset flip-flops in memory devices and computers, they have to be noise resistant. Now, again, these are kind of simulations it's impossible to do without a computer. So using MATLAB and Python, we can add noise to the system. And what's really remarkable with this is the system works very well with low amounts of noise. Obviously, the more noise we introduce, eventually there's so much noise that it gets swamped and it stops working. You know, it doesn't work anymore as a set reset flip-flop. But what is really, really remarkable, we haven't even published this result yet. When you add excessive amounts of noise, it comes back. It starts acting as a set reset flip-flop again. Now, we think that there could be applications with this, with NASA and with you know, radioactive things. So we think we can build our computers in space, and we don't have to worry about radiation because they are resistant to radiation. In week 6, I introduced students. So this is where we start doing discrete maps. So here's, I'm sure you've all seen the logistic map, and we can plot time series, show its sensitivity to initial conditions. And again, I give our students, the program to plot bifurcation diagrams for these systems. And this here is the really nice example of a complex iterative map, which is used to represent the propagation of light waves through a nonlinear simple fiber ring resonator. So this is called a nonlinear simple fiber ring resonator. So here you have optical fiber, the red lines, and in here, this represents your laser. So you fire your laser in. En is the electric field strength of the laser. A is related to input. B is related to the fiber coupling ratio. So how much light do you allow to circulate in the loop? And then we have the mod En squared is like the power. So what we can do then is we can simulate this system in the real world. So using Python and MATLAB, we can plot, and so this is a bifurcation diagram, but using what I call a second iterative method. So we increase the power in the laser. So imagine you've got a knob, you increase the power of the laser, and then we decrease it again. But obviously all of this is happening at the speed of light. So the blue curve there, sorry, the red curve here shows what happens when we increase the power of the laser. So we're on this steady state. Yeah, so we have, there's a steady state output power when we increase the power, and then we get to a point where there's a jump to a different steady state, and then we have period doubling bifurcations to chaos. Now, what's interesting is when we bring the input power back down, which is the blue curve, you'll see we come back down on a different path, and this is hysteresis. And this hysteresis loop is very important in computing because we can put a threshold value here, and this is where we can get our zeros and ones. And I've done lots of research to show that hysteresis is everywhere. If you have parameters increasing and decreasing, then in a majority of systems, the system is history dependent. And this has profound implications for all kinds of things. In week 10, I introduce our students to fractals and multifractals. This is a really nice example. So this gives you an example of how you can ask an examination question in a lab. So here is an example of where I give the students a full working program which shows them how to produce the Cantor set. So that, here's a full working Python program, and it gives you this picture here. So this is the standard Cantor set. What I can then ask the students to do in an examination environment is edit this program and produce a variation of the Cantor set where they remove the middle fifth segments. So instead of removing just the middle third segment and replace it with 2 segments, you remove the middle 2/5 segments and leave 3 segments. Okay, so you have to edit a certain number of lines in the code. But obviously, I don't tell them which lines they have to edit. Now, rather, typically with this kind of question, you ask the question where they have to edit 5 lines of code. Yeah, and so each edit, say, would be worth 2 marks. Or you could ask them questions. You can give them a full working program, and then you can ask them to put comments in. What is this part of the program doing? So that's another kind of question you could ask in an examination environment. As well as fractals, I introduced them to multifractals. So again, using Python and MATLAB, we can use image processing techniques to actually produce pictorial representations of these multifractals, and we can plot multifractal F-alpha spectra. So in this case, you'll see if we look at the numbers generated here, we have clusters of dark pixels because the majority of numbers are low. So you have clusters of darker pixels, and when we plot the F-alpha curve, you'll see the F-alpha curve is skewed left. If the grid that we use, if the numbers are all very similar to each other, then we get something called a homogeneous multifractal. So now it's started to look like a fractal. Small parts of the picture look like the whole picture. So we call that a homogeneous fractal. Unfortunately, most multifractals in the real world are heterogeneous, so they have a wide spread on the F-alpha spectrum. And then, if we have clusters of bright pixels, this is useful in the real world, because quite often microbiologists and chemists, etc., look at images and they want to measure clustering, dispersion, and density of material on surfaces. So again, now we're working with material scientists and surface chemists. And you'll see here, so that the height of the F alpha curve gives us a measure of density. The width of the F alpha curve gives us a measure of dispersion. And the asymmetry gives us a measure of clustering. So just with this one curve, we can get all of this information out. So you'll see over recent years, I've been working with microbiologists, material scientists, chemists, and I've got papers published in high impact journals. One thing that's really unfair with mathematics, I've had papers published in Procroy, SOC, nonlinearity, but all of those papers, the impact factor is like 2 and 3 and 1. If you publish papers in chemistry or material science, straight away the impact factor for those journals is 6, 7, 8, 9. So it's very unfair for us mathematicians. If you're interested in my research, I have a profile on ResearchGate. You'll see I've got nearly 117,000 reads. My ResearchGate score is 1800. On Google, on this, what was it called? Scholar GPS. As you see, I'm number 23 in the world for dynamical systems. I think you will all now be looking at what this Scholar GPS is and see what your scores are, where you're ranked, etc. So I have written books. So for people who are on this workshop who've never programmed before at all, then I recommend the first book, A Very Simple Introduction to Python. For those of you who have done a little bit of programming, you might have done a bit of programming with Maple or MATLAB, and you want to see how programming can be used in all of the, across the whole spectrum of STEM subjects and beyond, then I recommend the second book. And if you're interested in the dynamical systems with applications using Python, then this is suitable for final year undergraduate, but also postgraduate studies. So thank you very much for listening. I will stop sharing the screen, and I hope you all enjoyed the talk.
Okay, well, thanks for that, Stephen, and it's sort of great to sort of see so many, many examples that you built into your own teaching, your own experience, and I think interesting examples there of research-led teaching as a broader theme as well. I'm aware we need to sort of finish promptly, but there's a couple of questions in here. Please do, colleagues, feel free to drop some of those into the Q&A. But an interesting one here, and I think there's a lot of discussion around kind of diversity in assessment measures. Would a lab-based exam work as an online exam? So kind of for large cohorts, we don't have the lab capacity, but would there be some possibilities here, you think, Stephen, for using a lab-based exam?
Yeah, definitely. So MMU are just in the process of building a massive library. They've just got the funding to build a massive library, and there are going to be very large computer labs in there where there's no specialist equipment, on those machines. But because of Google Colab, we'll be able to have hundreds of students in the library, and they could just use Google Colab for the online assessments, or they could work from home. We could restrict them in time. Say you have 1 hour, to answer these questions with Google Colab, so they could do that. There are so many ways in which you can use Google Colab. Would also the advantage with Google Colab and GitHub, you can produce so university lecturers and teachers can produce their own web pages. So with these Jupyter notebooks, you can save them as HTML. And if you look at my web pages, you'll see I've produced notebooks which you can publish online.
Mm-hmm. Yeah, and some kind of interesting things here in that approach, recognizing that coding does involve engaging with those repositories, and Siri mentioned AI as well. That almost you kind of acknowledge that is part of the coding environment, and you can design your tasks accordingly. So you almost naturally mitigate against some of that, don't you?
Yeah. Yes.
Yeah. Brilliant. So I'll ask Alex's question, because that seems to follow on from that, which is, with Google Colab, do students use their own Google accounts, or do you have an institutional mechanism for this?
So we were using Google Colab with 350 foundation students, and every single one of those students had their own Google account. But I don't know. I suppose if there were some students who didn't want a Google account, I'm sure the university would be able to set up a certain number for those students who aren't happy, having their personal Google account. But none of our students, made any complaints about having a Google account.
Okay. I guess following on from that from Francis Stewart, who's in Toronto. How can we make dynamical systems accessible to GCSE and A-level students using Python? And I guess, Stephen, this is probably drawing on some of the things that you've kind of done through the IMA workshops on sort of Python. So maybe you could give us a bit of insight into your experience there.
That is a very timely question. So in September of this year, the IMA have got a Congress, AI and ML Congress workshop where they're inviting people from industry. So I'm on the organizing committee, and I've established a competition for AS level students. So what we're doing is I'm giving them a full working TensorFlow program used to predict time series. And these students will have to change 5 parameters in the model. So three of the parameters are the number of neurons in hidden layers. So we've got a long short-term memory, a recurrent neural network. There are 3 layers, 3 hidden layers so N1 neurons in the first layer, N2 neurons in the second layer, N3 in the third layer. There's also a learning rate, for the neural network, and the last one is the number of epochs. So there are only 5 parameters. So at the end of June, I'm going to run a workshop which will introduce school pupils to Python. So it's a 1-day workshop, Python for A-level mathematics and beyond. And at the end of that workshop, I will show them the problem. So they'll have the fundamentals of Python. They'll be able to use Python, just for simple commands. But then I will give them the full working program, the TensorFlow program. And before that, I will also show them the remarkable. I don't know if you've all seen how accurately TensorFlow and the deep learning toolbox can predict chaotic time series. Have you seen it, Michael? It's frightening. It's really frightening. If you look at if you look at the solutions to the second book, I ask, so you can use long short-term memory to predict the chaos in the Lorentz model, and it is extremely accurate. It's the first time you see it, you can't believe it, but it's extremely accurate. So obviously with the school pupils, to get them excited about it, we say, can we predict financial time series? Because they think they get jobs in the city and make lots of money, and indeed it does. Yeah, you can use long short-term memory, recurrent neural networks to predict future financial time series.
Yeah, and that's a nice example, Stephen, because it starts to sort of collect and chunk together different ideas that, they may not sort of be fully mathematically familiar with at that particular stage, but can actually deal with sort of computationally and numerically as well. So that's a sort of an interesting way of introducing it. So yeah, do look out for those things, colleagues, because I know Stephen's done a lot of kind of workshops around this through, for example, the IMA. The final question, and I will kind of end at that point, if that's okay, which is from Kawa, who says, in week 6 in Foundation Mathematics, so do you cover any kind of popular packages? If so, which one of those do you think is the most essential?
Week 6, I don't have to go back to week 6.
I think that's very, very specific for
in a foundation.
Yeah, or is it perhaps kind of, Stephen, just in general, what are the sort of popular packages that you would cover in that foundation course? Not necessarily week 6, save you trying to look this up.
Yeah, so we only introduce them to symbolic Python for maths, numerical Python, for arrays and artificial intelligence, and yeah, so it's only SymPy and Matplotlib. It's only those 3. Yeah, so we can do cryptography, we can do object-oriented programming, we can do artificial intelligence. We can do all of that just with those 3 libraries.
Brilliant. Stephen, I think after that you've certainly deserved a cup of tea or cup of coffee or whatever you may choose to do. I think that was a great talk. Equally, Siri, beforehand as well. I think you know, that was quite an extensive walk through of the number of things that you've done and embedded within practice. I think there was real diversity there. And similarly, Siri, you know, how you've embedded you know, Python within your own teaching within Warwick as well. So I think we'll end there. I think a plug or quickly a round of applause again for Stephen and Siri for their contributions today.